Today, we're going to work through the construction of the Great Pyramid of Giza, the largest, the most studied, and the most precisely built of all the Egyptian pyramids, using that evidence. We're going to go through it piece by piece, problem by problem, drawing on the most reliable archaeological findings, the most credible engineering analyses, and the most carefully tested experimental work available. Not aliens, not lost technology, not magic. The actual work of actual scholars working from actual evidence, argued seriously and tested where possible, refined over decades of serious investigation. Let's start with the numbers, because the numbers are where every honest conversation about the pyramids must begin. The scale of the problem. The Great Pyramid of Giza was built for the pharaoh Khufu, constructed over a period estimated at between 10 and 20 years, around 2560 BCE. It originally stood 481 feet tall. Its base covers 13 acres. It contains approximately 2.3 million stone blocks. Those blocks range in weight from about 2.5 tons for the standard limestone blocks that make up the bulk of the structure, to 15 tons for the granite blocks used in the internal chambers, to the largest known block in the pyramid, a granite slab in the king's chamber roofing, which weighs approximately 80 tons. If the pyramid was built in 20 years, the builders needed to place approximately 800 blocks per day. Some calculations suggest the number reached 200 per day during peak construction periods. 800 blocks. Every day, for 20 years. The workforce required to do this changed dramatically in the historical record in 1990, when a workers' village was discovered at Giza by archaeologist Mark Lehner. The village housed somewhere between 20,000 and 30,000 workers, not slaves, as was long assumed and as popular imagination still tends to assume, but paid labourers. Workers who were fed beef and fish and bread, whose medical injuries were treated, whose bones show healed fractures, evidence of a medical system capable of setting broken bones and providing recovery time. Their graffiti on the pyramid blocks includes team names like Friends of Khufu and Drunkards of Menkaure. This is not the labour of the enslaved. This is organised, managed, compensated work on an industrial scale unprecedented in the ancient world. The workers were organised into gangs, and the gangs into files, rotating crews that came from across Egypt, serving periods of labour as a form of tax payment to the state. But the engineering is what we're here to discuss. So let's start at the very beginning. The stone itself. Quarrying the stone. The Great Pyramid contains two main types of stone. The bulk of the interior is limestone, quarried from the Giza Plateau itself, essentially on site directly south of the pyramid. The outer casing, most of which no longer exists, having been stripped in the medieval period for use in Cairo's buildings, was fine white Tura limestone, quarried from across the Nile. The internal chambers and their roofing are Aswan granite, quarried 500 miles to the south. The on-site limestone quarries are still visible at Giza today. The marks of ancient tools are still in the stone. And from those marks, and from decades of experimental archaeology, we have a reliable picture of how this extraction was done. The Egyptians had copper, not iron, not steel, copper, which is significantly softer than the stone they were cutting. For much of the 20th century, this was considered a major puzzle. How do you cut hard stone with soft metal tools? The answer, demonstrated conclusively by experimental archaeologist Dennis Stocks, who spent years testing ancient Egyptian tool techniques, is that copper tools work, but not the way modern steel tools work. The copper saw is not dragged through limestone the way a steel saw cuts wood. Instead, the copper saw is used with an abrasive, quartz sand, introduced continuously into the cut as the saw moves back and forth. The sand does the actual cutting. The copper saw is the mechanism that keeps the abrasive in contact with the stone and moves it in a controlled direction. Stocks demonstrated through hands-on experimentation that copper tube drills and flat copper saws, used with quartz sand abrasive, could cut both limestone and granite at rates sufficient to explain the finished surfaces found throughout ancient Egyptian stonework. The marks left by these tools on ancient stone match the marks his replica tools left on modern samples. Beyond sawing, the Egyptians used splitting wherever possible. a far more efficient technique than cutting. The method was to cut a line of holes or channels along the intended fracture line, drive wooden wedges into those holes, and saturate the wedges with water. Wood expands when wet. The expansion force distributes along the fracture line and the stone breaks cleanly along it. This is not a hypothesis. The holes cut for the wedges are visible in unfinished quarry blocks throughout the Giza area. The physical evidence of this technique remains in the stone today, preserved in abandoned blocks that broke incorrectly and were left in place by their quarrymen. For the Aswan granite, the hardest material in the pyramid, the evidence points to an additional technique called pounding. Workers used balls of dolerite, an extremely hard igneous rock, to pound the granite surface repeatedly, grinding it down through sustained percussive impact. Dolerite balls have been found in large quantities at ancient granite quarrying sites throughout Egypt. The technique is slow and physically demanding, but it works on granite where copper tools alone are insufficient. The combination of these methods, copper tools sawing with sand abrasive, wedge splitting, and dolerite pounding for the hardest stone, constitutes a complete and internally consistent quarrying system that requires no mysterious or lost technology to explain. It requires only time, organization, and enormous quantities of human labor. Transporting the stone. Getting stone out of the quarry is only the first problem. Getting it to the pyramid, sometimes from 500 miles away, is the second. For much of the history of pyramid scholarship, transportation was considered among the most mysterious aspects of the project. It is considerably less mysterious now thanks to two discoveries in the past decade that fundamentally changed our understanding. The first was the discovery in 2013 of the Wadi El Jarf papyri, the world's oldest known papyri dating to the reign of Khufu himself. Among these documents is the journal of an official named Mera, who oversaw a team of approximately 40 men. Mera's journal records, in matter-of-fact administrative language, the transport of Tura limestone casing blocks by boat from the quarry across the Nile to a harbour near Giza called Rocher Khufu, the Lake of Khufu. From there, Mera's team moved the stone to the pyramid site via a canal system connected to the harbour. This is not speculation. This is a first-hand written account, contemporary with the construction, describing exactly how the stone was moved. It is one of the most significant archaeological discoveries in Egyptology in decades, and it confirms what engineers had long suspected. The Nile and a network of canals were the primary transportation infrastructure for pyramid construction. The second discovery was made at the alabaster quarry of Hatnub in 2014. Archaeologists uncovered a ramp system dating to the reign of Khufu, designed specifically for hauling heavy stone blocks up steep grades. The ramp had wooden post holes on either side and preserved sledge tracks in the center. Ropes attached to the sledge would be pulled by workers using the posts as anchor points, a simple pulley-like arrangement that multiplied the pulling force of the workers hauling the load uphill. Combined with the transportation scene depicted in the 2,000-year-old tomb of the official Jehutiotep, which shows workers pouring liquid in front of a sledge carrying a massive statue, the picture becomes clear. Workers hauled stone blocks on wooden sledges, pouring water ahead of the sledge as it moved. Wetting sand reduces friction dramatically, and this was confirmed by a 2014 study from the University of Amsterdam. The optimal moisture content for desert sand beneath a wooden sledge cuts the pulling force required by approximately 50%. The full transportation system worked as follows. For the bulk limestone quarried on the Giza plateau, the distance from quarry to pyramid was short. The quarry sits immediately south of the construction site. Workers moved these blocks on sledges over prepared surfaces of wetted sand and compacted earth. For the Tura limestone, blocks were loaded onto barges at the quarry, crossed the Nile, entered the canal system at the harbour, and were transported by water close to the pyramid base. For the Aswan granite, the journey was 500 miles north along the Nile, timed to the annual flood season when water levels were highest. At Giza, the granite was unloaded at the harbour and moved by sledge to the site. The logistics of the barge system are worth dwelling on. Moving an 80-ton granite block on a river barge requires a barge of considerable size and structural integrity. No such barges from this period have survived, But ancient Egyptian texts describe large cargo vessels, and the mathematics of floating such loads is straightforward. Wood floats regardless of what it is carrying, and a barge of sufficient length distributes the load across enough water displacement to remain stable. Egyptian shipbuilders of the Old Kingdom were sophisticated craftsmen whose vessels were capable of exactly this. The harbour and the causeway. The Wadi El Jarf papyri describe Mera's stone being delivered to the Lake of Khufu, a harbour associated with the pyramid complex. This was not an accident of geography. The Egyptians built the harbour deliberately, and they built a causeway connecting it to the pyramid plateau. The Giza Causeway, the ancient road that connected the Valley Temple at the base of the plateau to the pyramid complex at its summit, is partially preserved and well documented. It ran for approximately half a mile and was paved with limestone, wide enough for sledges carrying large blocks. Along its length, workers could haul stone from the harbour level to the plateau level without navigating unprepared terrain. Examination of the plateau itself reveals additional infrastructure that the Egyptians installed for the construction project. Post holes and groundwear patterns consistent with sledge traffic have been identified in the quarry areas. The plateau was shaped and levelled in preparation for construction, with the natural limestone bedrock serving as the foundation for the pyramid, a crucial engineering decision that guaranteed stability on a scale that no imported foundation material could have matched. The level of logistical planning represented by the harbour, the canal system, the causeway, and the prepared plateau is remarkable. The construction of the pyramid was not simply a project of lifting stone. It was a complete infrastructure project, a supply chain of extraordinary complexity built specifically to support the construction and dismantled or repurposed when the construction was complete. Preparing the site and laying the foundation. Before the first block could be placed, the site had to be prepared with a precision that remains breathtaking 5 millennia later. The Great Pyramid's base is level to within 2.1 centimeters across its entire 230-meter span, a tolerance that a modern construction team using laser levels would consider excellent. Its sides are oriented to the cardinal directions with an accuracy of less than 0.05 degrees. Its corner angles deviate from perfect right angles by less than 0.09 degrees. These tolerances were not achieved by accident. They required deliberate, skilled surveying using the tools available in 2560 BCE. For leveling the base, the most reliable reconstruction involves water channels. A network of channels cut into the bedrock of the plateau, filled with water, provides a perfectly level reference surface. Water, by definition, finds its own level. The perimeter of the base could be aligned to the water level in these channels with considerable precision. Evidence for this technique sits in the plateau itself. Channels cut in the bedrock around the pyramid's base are still visible, and their dimensions and arrangement are consistent with a water-based leveling system. For the orientation to the cardinal directions, astronomical observation was the tool. The astronomer Kate Spence demonstrated in a 2000 paper published in Nature that by observing the simultaneous transit of two circumpolar stars, Mizar and Kochab, which aligned with the celestial North Pole around 2478 BCE, the builders could establish a true north line to within 0.05 degrees of accuracy. This matches precisely the observed orientation error of the Great Pyramid, and the technique requires no instruments beyond careful naked-eye observation and a simple sighting tool. The merkhet, an ancient Egyptian astronomical instrument consisting of a plumb line and a palm rib with a slot cut in it, is documented in Egyptian sources as a tool for nighttime astronomical observation. Its use for establishing cardinal directions is entirely consistent with the precision achieved, and examples of merkhets survive in museum collections. Once the base was leveled and oriented, the first course of blocks was laid on the bedrock foundation. The natural limestone outcrop at the center of the pyramid's footprint was left in place. It rises to approximately 20 feet above the base level and saves the labor of filling the center of the pyramid's lower courses with quarried stone. Building the pyramid. The ramps. The question that has dominated pyramid scholarship for over a century, that has generated more competing hypotheses and more dramatic experimental tests than any other aspect of the construction, is this: How did the Egyptians lift 2.5-ton blocks and 80-ton granite slabs to heights exceeding 400 feet? The answer almost certainly involves ramps. The physical evidence for ramp construction at Egyptian pyramid sites is extensive. Ramp remains are preserved at multiple sites, including the unfinished pyramid of Sekhemkhet, the pyramid of Meidum, and various quarry sites. Egyptian workers clearly built ramps of mud brick, rubble, and compacted sand. The question is the configuration of those ramps as the pyramid grew. The straight external ramp, a single ramp built on one face of the pyramid, extended upward as the structure rose, is the simplest hypothesis and the one with the longest scholarly history. Workers would haul blocks up this ramp on sledges, placing each successive course of stone from the top of the ramp. The technique works for the lower portions of the pyramid. The Hatnub ramp demonstrates that Egyptian workers could haul heavy blocks up ramps at gradients of approximately 8 to 10%, steep enough to be practical, shallow enough to allow effective hauling. At the lower levels of the pyramid, a straight ramp of this gradient is geometrically reasonable and requires no materials beyond what was available. The problem appears as the pyramid grows higher. A straight ramp maintaining an 8% gradient that reaches the top of the Great Pyramid at 481 feet would need to be approximately 1 mile long. The volume of material in such a ramp would exceed the volume of the pyramid itself. The ramp would be a larger construction project than the structure it was built to construct. While this is not physically impossible, it seems extraordinarily inefficient, and the logistics of demolishing a mile-long ramp after completion would be nearly as complex as building it. The most compelling resolution to this problem, and the one that has gained the most serious engineering support, is that the Egyptians used the straight external ramp for the lower portion of the pyramid, roughly the bottom third where the geometry is manageable, and then transitioned to a different system for the upper portion. The system most supported by physical evidence for the upper stages is a wrapping or zigzag ramp built against the outer face of the pyramid itself. Rather than one straight ramp extending outward from the structure, a series of shorter ramps would have zigzagged up the pyramid's faces, switching direction at each corner and rising progressively around the structure. The footprint of such a ramp system is far smaller than a straight ramp. The material requirement is dramatically reduced. The ramps would be built in sections, with completed sections below being filled in with rubble and casing stone as the work progressed upward. The strongest physical evidence for this approach comes from microgravimetry surveys of the pyramid conducted in 1986 by a French team, which detected a spiral anomaly in the density of the upper portion of the pyramid, a continuous passage or less dense zone spiraling within the outer casing. This anomaly has not been conclusively explained by the conventional ramp hypothesis and is consistent with the remains of an internal or near-surface ramp structure that was filled during or after construction. More recently, the Scan Pyramids project, an international collaboration using muon tomography, thermal imaging, and 3D reconstruction technology, has been scanning the interior of the Great Pyramid at unprecedented resolution. In 2017, the project announced the discovery of a large, previously unknown void above the Grand Gallery, a space approximately 30 meters long and of uncertain purpose. The full publication of the Scan Pyramids data is ongoing, and further structural anomalies may yet clarify the internal organization of the pyramid and the ramp question with it. For the largest granite blocks, the 80-ton slabs roofing the king's chamber, the ramp system alone is insufficient. These blocks needed to be raised to a height of approximately 175 feet. The most plausible mechanism for placing them, given their weight, involves a combination of the ramp system for horizontal movement and a series of wooden rockers or levers for the final vertical placement. Experimental archaeology has demonstrated that a team of workers using long wooden levers can raise a large stone block incrementally, rocking it onto successively higher wooden platforms, at rates consistent with the construction schedule. The technique is slow and requires considerable coordination, but it is mechanically sound. Fitting the blocks. Moving blocks to the pyramid solves only part of the problem. Fitting them together with the precision the pyramid displays is another challenge entirely. The outer casing stones of the Great Pyramid, The fine Tura limestone blocks that formed its smooth white exterior were fitted together with joints so tight that a piece of paper cannot be inserted between them. The adhesive used in these joints has been analysed and identified as a gypsum-based mortar. But the mortar's role was not primarily structural. It functioned as a lubricant during placement, allowing the stone to be slid into final position, and then as a filler that prevented the movement of grit and debris into the joint afterward. The stones were cut precisely enough that the mortar bears essentially no load. The weight is transferred stone to stone. The cutting of the casing stones to this precision used the copper saw and sand abrasive technique. The final faces were ground and polished, using abrasive stones worked in circular patterns, the same technique used in Egyptian stonework throughout the period. Surviving casing stones, displaced from the pyramid and excavated from the debris around its base, show the same surface characteristics as other finely finished Egyptian stonework, confirming that the casing was produced using known Egyptian techniques. The interior of the pyramid was built to lower tolerances than the exterior. The core blocks are not cut to the precision of the casing, and their joints are wider and less consistent. This is exactly what you would expect from a rational construction program. The highest precision work concentrated where it is visible and where structural integrity demands it, with less precision in the interior where neither condition applies. The internal chambers and passages. The internal structure of the Great Pyramid is more complex than its exterior suggests. It contains 3 chambers: the subterranean chamber cut into the bedrock below the pyramid, the Queen's chamber at roughly the pyramid's mid-level, and the King's chamber near the center of the mass, connected by passages of considerable precision. The Grand Gallery, the ascending passage leading to the King's chamber, is one of the most remarkable interior spaces in ancient architecture. It is 153 feet long, 8.5 feet wide, and 28 feet tall, with corbelled walls that step inward as they rise, creating a vaulted effect. The corbelling distributes the weight of the stone above the passage outward into the pyramid's mass, preventing the ceiling from collapsing under the enormous load pressing down from above. This is not intuitive engineering. The understanding that a corbelled vault distributes load laterally rather than directing it downward onto the ceiling requires either a sophisticated grasp of structural mechanics or accumulated empirical knowledge from previous construction experience. And the Egyptians had both. The architectural tradition that produced the Great Pyramid had been developing for generations, with each major pyramid building program informing the next. The King's chamber roofing is perhaps the most sophisticated structural solution in the pyramid. Above the chamber ceiling are 5 relieving chambers, hollow spaces stacked one above the other, topped by a pointed limestone roof. The purpose of this system is to redirect the weight of the approximately 500,000 tons of stone above the chamber away from the chamber ceiling and into the pyramid's mass on either side. The chamber ceiling itself is not load-bearing. The relieving chambers ensure that the load is distributed before it reaches the ceiling blocks. This structural solution was not obvious. It required the designers to anticipate the distribution of loads through a stone mass of unprecedented size, to recognize where failure was likely to occur, and to engineer a preventive solution before the problem manifested. The pyramid has now stood for 4,500 years without the King's chamber ceiling failing. The engineering was correct. The finishing, casing, and capstone. The outer surface of the completed pyramid was finished with the Tura limestone casing stones, polished, angled precisely at 51.5 degrees to form the smooth sloping faces. The work of applying the casing was done from the top down. As the pyramid reached its final height, workers began casing the uppermost courses first and worked downward, with the ramp system being progressively dismantled as the casing was completed below the current working level. The capstone, the pyramidion, was the final piece placed. No capstone from the Great Pyramid survives, but pyramidions from other pyramids do, and they are typically made of granite or fine limestone and sometimes covered with electrum, an alloy of gold and silver, to catch the first and last light of day. The placement of the pyramidion was almost certainly a ceremonial occasion as well as a construction milestone. Once the casing was complete and the ramp material removed, the pyramid would have appeared as it was designed to appear. A blinding white geometric form rising from the desert plateau, its polished surface reflecting the Egyptian sun with an intensity that ancient texts describe as visible from considerable distances. The Arab historian al-Masudi, writing in the 10th century CE, described the Great Pyramid as appearing to glow. He was writing from accounts of a pyramid that still retained most of its casing. The building that stands at Giza today, stripped of its casing, eroded by time, is not what Khufu saw when the project was complete. What this tells us: the accumulated evidence, the workers' village, the Wadi el-Jarf papyri, the Hatnub ramp, the tool marks in the quarry, the microgravimetry scans, the experimental archaeology, the structural analysis of the chambers, tells a consistent story. The pyramids were built by a highly organized state deploying a large, competent, compensated workforce over an extended period, using a toolkit of copper and stone and wood and rope and water that, while materially simple, was deployed with a sophistication of technique and a depth of empirical knowledge that we have consistently underestimated. There was no lost technology, there was technique, skilled, accumulated, refined through generations of practice and transmitted through the apprenticeship relationships that are how all craft knowledge moves from one generation to the next. The Egyptians did not need anything we don't have. They needed knowledge, organization, time, and the particular kind of institutional will that only a state with the resources of ancient Egypt could sustain across 2 decades. They also needed something that is harder to quantify, but no less important: belief. The pyramid was not merely a construction project, it was a cosmological statement, a physical embodiment of the Egyptian understanding of the universe, a monument designed to house the body of a man who was understood to be a god, and whose successful transition to the afterlife was understood to be essential to the continued order of the world. The workers who placed those 2.3 million blocks were not simply doing a job. They were participating in something that their entire civilization told them was the most important thing happening in the world. That does not explain the engineering, but it helps explain the sustained commitment of labor, resources, and organizational energy that the engineering required. The pyramids are not mysterious because they required something we can't account for. They are extraordinary because they demonstrate what human beings can accomplish when they organize themselves with sufficient purpose around a goal that matters enough to them to sustain the effort across time. That is not a comfortable explanation because it doesn't leave us anywhere to hide from what it implies. What human beings built, human beings built. And that is more astonishing, not less, for being true. The Great Pyramid of Giza remained the tallest man-made structure on Earth for 3,800 years, from its completion around 2560 BCE until the construction of Lincoln Cathedral in England around 1311 CE. For 3,800 years, nothing human beings built was taller. Built with copper tools, built with wood and rope and water and sand, built by people. If you watched this far, let me know where you're watching from. Consider leaving a like and subscribing to the channel. See you next time.